welcome to the deep dive.
Okay, great to be here.
All right. So we've got some really interesting stuff to talk about today, right?
Yeah.
You've been sending over some fascinating stuff about this new way to basically get the best of all worlds when it comes to AI models, right?
Right.
So the idea of like model merging or getting, the strength of multiple AI models into one without sort of the usual downsides,
Yeah.
like complexity, extra training time, things like that.
Exactly. Yeah.
You've shared some fascinating material about a new approach to this, and we're going to dive deep into what makes it different and why it could be a game changer. We'll be primarily looking at a research paper introducing something called reinforced model merging, or RMM, which tackles some of the existing challenges in combining AI models. Our goal today is to unpack what RMM is, how it works differently from other methods you might have heard about, and what the potential benefits are, all without getting bogged down in technical jargon. Really exciting stuff here, especially like, this new technique, how it kind of aims for efficiency and overcoming limitations of older techniques.
Yeah.
So I guess to start off, like, why would anyone want to merge models in the first place? It sounds kind of like a pain.
Yeah. Well, you can think about it this way. Let's say you have an AI model that's really good at, I don't know, let's say recognizing different species of birds.
Okay.
And then you have another AI model that's really good at, let's say, summarizing news articles.
Oh.
So you might want a single AI model that's good at both of those things.
Right.
And traditionally, you would have to train a whole new model
Yeah.
from scratch
Yeah.
on a data set that includes both images of birds and news articles.
Right.
And that takes a lot of time, a lot of computational resources.
Yeah.
Plus, there's also a risk that when the bird expert model is learning about news, it might forget some of what it knows about birds. This is a phenomenon called catastrophic forgetting. So model merging offers a more efficient alternative where you can basically take these existing highly skilled task-specific models and you can combine them into a single model.
I see. So you don't have to start from like zero every time. You don't have to go back to like, AI kindergarten.
Exactly, yeah.
Yeah.
You can just leverage this existing expertise.
Yeah. So the paper you shared mentions, there have been different ways of doing this kind of model merging in the past. So what did the earlier attempts look like? What were they doing?
Yeah, so earlier attempts, a lot of them fell under this category of what's called knowledge amalgamation.
Okay.
And these methods usually involve some form of, additional training
Yeah.
after the initial models are created. But more recently, there's been, a shift toward what are called training-free merging methods.
Training free.
Yeah, and as the name suggests, these methods combine models directly in their parameter space
Mhm.
without any need for further training. So they offer a huge boost in efficiency.
So that's pretty amazing.
Yeah.
So then if this training free merging is so great, why do we need this RMM?
Yeah.
What are the kind of drawbacks?
Yeah. So the main challenge with current training-free methods arises when you try to merge models that were trained on very different tasks.
Okay.
What the paper describes as vast domain gaps.
Okay.
So going back to our bird image model and news summarization model, the bird image model has learned about shapes and colors and textures.
Visual stuff.
Yeah, exactly. Visual features. And the news model has learned about grammar and vocabulary.
The language.
Yeah, exactly. Language stuff.
Yeah.
So if you just try to merge their parameters uniformly, across the board, you often end up with a combined model that doesn't perform as well on either task.
Oh.
And this is because these models have developed what's called heterogeneous knowledge. So basically, the way they've internally organized information is tailored to their specific tasks.
I see.
Yeah.
Okay, so it's not just a simple like, cut and paste or like a direct translation thing.
Exactly. Yeah.
Okay, so the paper also mentions like this other category of methods called search-based methods.
Yeah.
What are they doing?
Yeah, so search-based methods attempt to find better ways to combine models by basically trying out different combinations of their parts.
Okay.
But the major drawback here is efficiency.
Okay.
To determine if a particular merged model is any good, you typically have to evaluate it on entire data sets,
Right.
which we know can be very time-consuming.
Yeah.
And the paper also points out that these search methods tend to be quite rigid
Okay.
and may not adapt well to a wide variety of merging scenarios.
Okay. So we've got the core problem here that merging models is a great way to get more versatile AI.
Right.
It's hard to do well. especially when the original models are like really good at different things.
Right.
The training-free stuff can lead to drops in performance, and search-based stuff is slow.
Oh,
So this brings us to RMM.
right.
So tell us, what's the central idea? How does it try to solve these problems?
Yeah, so RMM introduces this flexible and effective framework. They model this model merging task as a decision-making process
Okay.
by an agent.
Okay.
So basically, they have this agent that tries to figure out the best way to merge the models layer by layer.
Okay.
Within what they call an extensible environment.
Yeah.
And it does all of this automatically.
Hmm.
Yeah, so it's not just a, one-size-fits-all approach.
Yeah.
It's more like it's more intelligent. It's
Yeah.
like, carefully constructing the merged model piece by piece.
Oh.
Yeah.
Okay.
And a crucial point here is that RMM achieves this without any gradient computations.
Gradient computation.
Yeah, on the original models.
Okay.
Now, gradient computations are like the heavy lifting in AI training.
Okay.
So by avoiding these computations, RMM becomes much more efficient
I see.
and potentially suitable for devices with limited computing power,
Okay.
what are often referred to as edge devices,
Okay.
like smartphones or embedded systems.
So not just clever, but also designed to like work in environments where you don't have unlimited, supercomputer power.
Exactly. Yeah.
Okay. So how does this agent actually make these merging decisions?
Yeah.
What guides it?
Yeah. So that's where the reinforcement part of reinforced model merging comes in.
Okay.
So the agent learns what to do by receiving rewards based on how well the merged model is performing.
Okay.
So as it makes a decision about how to combine a particular layer,
Yeah.
it gets feedback on the quality of the resulting merged model.
Okay.
And to make this feedback loop much faster, they've come up with this mechanism called dynamic average reward, or DAR.
DAR.
Yeah.
Okay.
And this is a really ingenious idea that avoids having to test the merged model on the entire data set every single time.
Oh, okay.
So instead, it uses only a small subset of the data to get, a quick estimate of performance, which significantly speeds up the reward feedback process.
So it's getting like a sneak peek
Yeah, exactly.
of how good it's doing.
Exactly, yeah.
It doesn't have to go through the entire testing set every time.
Yeah, exactly, yeah.
Okay, so that makes sense. So it's getting like this kind of quick signal of like, are we on the right track or not?
Exactly, yeah.
Okay, so let's get into like the nuts and bolts, I guess, of how it actually works.
Yeah.
We've got this merging agent, and it operates within this merging environment.
Right.
So what are the kind of key pieces of each of those?
Yeah, so let's start with the merging agent.
Okay.
So its main role is to basically browse through the layers of the different models that we want to merge.
Okay.
And it does this one layer at a time.
Okay.
And at each layer that it's considering, it gets what's called a state
Okay.
from the environment.
Okay.
And then based on the state, it chooses a merging action.
Okay.
And the paper highlights 3 main types of actions that this agent can take.
Okay, so the agent is looking at each layer and then deciding what to do with that layer.
Exactly, yeah.
Okay, what are the actions? What can it do?
Yeah, so the first type of action is called a model action.
Okay.
And this is where the agent can decide to simply take the parameters
Okay.
directly from one of the original individual models. So the idea here is to ensure that the merged model retains some of the specialized knowledge that made the original models good at their specific tasks.
Okay.
So it's not just uniformly blending everything.
Yeah.
It's about preserving what works well.
Yeah. So sometimes instead of trying to blend, keep it separate.
Exactly. Yeah.
Okay.
Yeah. If it's beneficial.
Makes sense. What's the second action?
Yeah. So the second type of action is called a merging action.
Okay.
And this is where the actual combining of knowledge happens.
Okay.
So here the agent can choose to apply existing what are called model merging operators.
Or merging operators.
Yes.
Okay.
And the paper specifically mentions task arithmetic and ties merging as examples of these.
Okay.
And these are established techniques that have been shown to be effective at combining knowledge from different tasks.
Yeah.
So RMM can strategically use these existing, blending methods.
Yeah.
When it makes sense to combine information, across the original models.
So the first one is like keeping things separate when it's good.
Right.
And the second one is intelligently blending them using existing techniques.
Exactly. Yeah.
What's the third action?
Yeah. So the third type of action is called a layer action.
Okay.
And this adds another level of sophistication to the process.
Okay.
So drawing inspiration from some previous research, RMM allows the agent to either skip the current layer,
Okay.
and move on to consider the next one.
Okay.
Essentially creating jump connections in the architecture,
I see.
or back to a previous layer to reconsider it.
Okay.
Allowing for a kind of hierarchical way of stacking knowledge. Now, it's important to clarify that these layer actions, they don't directly change the parameters of the model at that specific layer.
Okay.
Instead, they control which layer the agent will focus on for its next decision.
I see. So it's not like it's making a decision about that layer.
Right.
It's just like deciding which layer to consider next.
Exactly. Yeah. It's more like, it has the ability to kind of strategically navigate the architecture of the models.
Okay, so it can skip ahead, it can go back.
Yeah.
So it's not just making a decision about each layer like in a vacuum. It's also like, how it's navigating through the whole set of layers.
Exactly.
Okay. Now let's talk about the merging environment that this agent is operating within.
Yeah.
So what kind of information does it provide to the agent, and how does it track this whole merging process?
Yeah, so the merging environment is what provides the agent with what's called the state information. Okay.
That it needs to make informed decisions.
Okay.
And this state is represented as what's called a matrix merging map.
A matrix merging map.
Yeah.
Okay.
So you can think of this as a kind of dynamic blueprint that shows the agent what merging decisions have been made so far for each layer.
Okay.
And which layer is currently being considered. So as the agent takes an action, whether it's a model action, merging action, or layer action, this merging map is updated to reflect that decision. Mm-hmm. So it's essentially keeping track of the agent's progress.
I see.
In constructing the merged model.
It's like a plan, like an evolving plan.
Exactly. Yeah.
Okay. And
then once the agent has gone through all the relevant layers and made its sequence of decisions, the environment then takes this blueprint
and assembles the final merged AI model from these optimally combined layers.
Yeah.
And as we discussed earlier, the environment is also responsible for calculating the reward that the agent receives.
Yeah.
By evaluating the performance of the merged model.
Yeah.
On various relevant data sets, using appropriate metrics.
Okay. So it's kind of like the agent's picking a move. The environment is kind of updating the plan and then testing the result.
Exactly. Yeah.
Okay.
It's like a game.
Yeah. It's like this game where it's like, how well did you do?
Yeah.
Okay. And then this thing, RL optimization, PPO. Can you break down what that means?
Yeah. So because the ultimate goal is for the agent to find the best sequence of merging actions, and the outcome of these actions, the performance of the merged model, is not something you can directly compute. The gradients of they use what's called reinforcement learning, or RL, to train the agent's decision-making process.
Okay.
And specifically, they employ a particular RL algorithm called proximal policy optimization, or PPO.
PPO.
Yeah. And this is what's called an off-policy method.
Okay.
Which basically means that the agent can learn from past experiences, even if those experiences weren't generated by its most recent strategy.
I see.
Yeah.
Okay. So it can learn from learn from like its mistakes, basically.
Exactly. Yeah.
Okay.
And refine its merging strategy, over time.
Okay.
And within this PPO setup, the agent has two main components: what's called an actor and a critic. Okay.
So the actor is responsible for deciding which merging action to take
Okay.
at each layer. So it's the part that makes the decisions.
Yeah.
The critic, on the other hand, it tries to estimate how good it is to be in the current state.
Okay.
So it evaluates the potential future rewards that the agent might receive.
Okay.
And by having both an actor and a critic, PPO allows for efficient learning because the agent can reuse the data it collects from trying out different merging strategies.
Yeah.
To update both its decision-making policy, which is the actor,
Yeah.
and its evaluation of the situation, which is the critic, multiple times, which speeds up the overall learning process.
Okay.
Yeah.
So we've got the agent making decisions,
Yeah.
the environment's giving it feedback.
Yeah.
And then this reinforcement learning is kind of guiding it toward better strategies. Exactly.
Okay.
Yeah.
The paper goes on to talk about a bunch of experiments that they did,
Right.
both in like computer vision and natural language processing tasks.
Yeah.
So what were the key findings from those experiments?
Yeah. So the results were really impressive. So for the vision experiments, they used several standard image classification data sets, like CIFAR 10, CIFAR 100,
Right.
CUB 200, and Stanford dogs.
Okay.
And these are all basically about training models to correctly identify different objects and categories within images.
Okay.
And they used popular vision transformer models as their base model.
Vision transformer models.
Okay. Which are a state-of-the-art type of neural network for image processing.
Okay.
And when they compared RMM's performance to several existing model merging techniques, such as weight averaging, task arithmetic, ties merging, and DARE.
They found that RMM consistently achieved better results with average improvements of over 4% and 7% in accuracy.
Okay.
For the two different vision transformer models that they tested, and notably on some of the more common image recognition tasks, RMM actually outperformed the previous best merging methods by a significant margin.
Oh, wow.
Yeah.
Okay, so that's a solid kind of step forward on well-established tasks.
Yeah.
But the paper also highlights these results on what they called fine-grained merging.
Right.
So what made those experiments particularly noteworthy?
Yeah, so the fine-grained merging experiments were especially interesting because they involved merging models that had been trained on the CUB 200 and Stanford dogs data sets.
Okay.
And these are described as entirely distinct species classification tasks.
Meaning the models had to learn to distinguish between hundreds of very similar looking types of birds or dogs.
Right.
Based on the subtle visual differences.
Yeah.
And the paper points out that traditional merging methods really struggled with these kinds of tasks.
Okay.
With the performance of the merged models dropping to nearly half of what could be achieved by fine-tuning a model specifically for those data sets.
Oh, wow.
However, RMM showed a remarkable improvement in performance here, achieving boosts of up to 21% and 7% on these data sets.
Okay.
Which strongly suggests that RMM is much better at handling the complexities of combining knowledge when the original models have learned to recognize very different and nuanced features.
So this really showcases RMM's ability to kind of bridge these gaps that we were talking about.
Exactly. Yeah.
These big differences between what the models were trained on originally.
Yeah.
So imagine you have like an AI that's an expert in recognizing breeds of dogs.
Right.
And then another one that's an expert in types of birds.
Yeah.
And now you can combine those and it's surprisingly good at both.
Exactly. Yeah.
That's the kind of potential that this seems to unlock.
Yeah.
So what about the experiments in NLP and natural language processing?
Yeah.
Did they see similar benefits there?
Yeah, so for NLP, they used a diverse set of 7 data sets, covering various tasks like question answering, paraphrase identification, sentence completion, and conference resolution.
Okay.
And they grouped these into QA tasks and mixed NLP tasks.
Okay.
And they used the T5 family of transformer-based language models as their base models, which are also state of the art in the NLP field.
Okay.
And similar to the vision experiments, RMM demonstrated significant performance gains compared to the baseline merging methods,
Okay.
achieving around 10% and 7% average improvements on the 2 different T5 models that they tested. And what's particularly noteworthy here is that they were able to achieve these improvements even when using only a tiny fraction, just 1% of the training data to evaluate the merged models.
Okay.
So this again highlights the efficiency and robustness of their approach in a completely different domain.
So it's not just better performance, but it's also like doing it in a way that requires like significantly less data
Exactly.
for the merging process itself.
Exactly. Yeah.
Okay, so the paper mentioned something called an ablation study on DAR.
Yeah.
So what was the purpose of that, and what did it reveal?
Yeah, so the ablation study was specifically designed to investigate the impact of their dynamic average reward or DAR mechanism,
Okay.
which as we discussed, is key to their efficient reward feedback.
Yeah.
So they tested RMM's performance using different amounts of data for evaluation, 100%, 10%, and just 1%.
Okay.
And compared the results with and without using DAR.
Okay.
And the key finding was that DAR indeed plays a crucial role in helping RMM perform better,
Right.
especially when only a small amount of evaluation data is available. So it not only led to average accuracy improvements, but it also helped to make the reward feedback during the agent's learning process more stable and reliable.
Okay.
Yeah.
So it's not just about speed, but it's also contributing to the overall like effectiveness and stability of the whole process.
Right. Exactly. Yeah.
Especially when data's scarce.
Yeah.
Okay, and then finally, the paper makes some pretty impressive claims about like the speed at which models can be merged
Right.
using this technique.
Yeah.
So what's going on there?
Yeah. So the acceleration aspect is one of the major highlights here.
Okay.
With significant practical implications.
Okay.
So as we've discussed, RMM avoids these computationally intensive gradient calculations on the original models.
Yeah.
And when you combine this with with their DR mechanism, which allows for performance evaluation using only a small fraction of the data.
Yeah.
They achieved remarkable time savings.
Okay.
So they found that with just 1% of the data, they could merge models in a matter of minutes, about 0.04 hours.
Okay.
Or less than 3 minutes, with virtually no noticeable decline in the performance of the resulting merged model.
Okay.
And this translated to a speed up of approximately 100 times.
100 times.
Yeah.
Wow.
Compared to more traditional search-based merging methods that that require evaluating on the full data set.
So basically like less than 3 minutes to merge complex AI models.
Yeah.
With almost no loss in performance.
Exactly.
And like 100-fold increase in speed.
Yeah.
That's huge.
Yeah.